Welcome, everyone. Today's topic is an absolute favorite of mine. We're going on a fascinating journey to explore the microscopic universe hiding inside every single atom. We're going to break down the incredible architecture that dictates how matter itself is built, right down to the fundamental rules that govern the universe at its absolute smallest scale.
But before we get into the heavy stuff, let me ask you, what does an atom actually look like? For a lot of us, the first thing that pops into our heads is a tiny, solid sphere, kind of like a microscopic billiard ball. But as we're going to see today, that preconceived notion is completely different from the breathtaking reality. Here's our roadmap for today. 1. Early models. 2. Rutherford's discovery. 3. The cosmic address. 4. Rules of the orbital house. 5. Orbital shapes and nodes. And finally, 6. Exceptions to the rules.
Section 1. Early Mortals.
Okay, let's dive right into this. On one side, we had J.J. Thomson's early concept. He imagined the atom kind of like a watermelon, a solid, uniform sphere of positive charge, with negative electrons embedded in it just like seeds. I mean, it made sense at the time. But then came the reality uncovered by Ernest Rutherford. Rutherford completely shattered that watermelon model, proving that the atom is actually mostly empty space, with a tiny, unbelievably dense nucleus at the very center. So how did he actually prove this?
Section 2. Rutherford's discovery.
So, Rutherford fired these positively charged alpha particles at an incredibly thin sheet of gold foil. Now, if Thomson's watermelon model was right, those particles should have blasted straight through that soft, uniform positive charge. And guess what? 99% of them totally did. But here is the mind-blowing part. Roughly 1 in a million particles violently bounced straight back. Rutherford was completely stunned. He said it was like firing a massive artillery shell at a piece of tissue paper and having it bounce back to hit you. This proved, without a shadow of a doubt, that a super dense, tiny positive nucleus was sitting right there in the dead center of the atom.
Section 3. The cosmic address.
All right, so the nucleus is in the center, and the electrons are on the outside. But where exactly are these electrons? Welcome to the core concept of quantum mechanics. Think of finding an electron just like finding a friend's house. Step 1 is the principal quantum number. Think of that as the city. Let's say Delhi. Step 2 is the azimuthal number. That narrows it down to the exact neighborhood, like Pitampura. Step 3 is the magnetic quantum number. That's the specific block or house. And finally, step 4 is the spin, which tells you exactly which roommate you are looking at inside that house. Let's break these down. First up is the city, or the principal quantum number, represented by the letter N. This dictates the main energy shells orbiting the nucleus, traditionally labeled K, L, M, and N. As N goes from 1 to 2 and then to 3, the shell gets bigger. We can actually calculate the absolute maximum number of electrons a shell can hold using a brilliantly simple formula, 2n squared.
Now, inside that city, we need the exact neighborhood and house. The azimuthal and magnetic quantum numbers define these subshells, labeled S, P, D, and F. Notice the pattern in the number of orbitals, or rooms. It's a clean sequence of odd numbers. The S subshell has 1 room, P has 3, D has 5, and F has 7 rooms. This tells us exactly how much space is available in that specific neighborhood.
And finally, the roommate dynamics. The spin quantum number tells us that every single room or orbital holds exactly 2 electrons. But they can't be identical twins. One spins clockwise, mathematically represented as +1/2, and the other spins anti-clockwise, -1/2.
Section 4. Rules of the orbital house. So the crucial point is this. Now we know where they live, but how do they actually fill up these rooms? Well, nature is incredibly efficient and always prefers the path of lowest energy. The 2 governing laws of configuration explain this perfectly. The Aufbau principle states that electrons fill lower energy subshells first. So they start at 1s, then go to 2s, then 2p. Then we have Hund's rule, which tells us how electrons behave once they get into a subshell with multiple rooms, like the p subshell with its 3 distinct rooms.
To really understand Hund's rule intuitively, think about it like this. If a mom has 3 rotis for her 3 hungry kids, she gives 1 to each before giving anyone seconds, right? It just maintains peace and stability. Electrons do exactly the same thing. If you have 3 empty rooms in a p orbital and 3 electrons arrive, they won't bunk up together right away. They'll take 1 room each to maintain maximum stability. It's only when a 4th electron arrives that they'll start pairing up.
Section 5. orbital shapes and nodes.
We've been using this analogy of rooms, but physically, what does this actually look like? Geometrically, the s orbital is perfectly spherical, like a hollow ball around the nucleus. The p orbitals look like dumbbells stretching across the x, y, or z axes, which, by the way, is exactly why they are named px, py, and pz. The d orbitals are even more complex double dumbbells, and there's one really cool rebel in there, dz squared, which basically looks like a dumbbell wearing a donut-shaped ring around its center.
But here is a fascinating quirk of quantum mechanics. In between all these shapes are things called nodes. These are literal dead zones within the atom. Despite the electron moving at blinding speeds everywhere else, there are specific angular planes and radial spheres where the probability of finding that electron drops to absolute exact zero. They simply cannot exist in those dead zones. It's wild.
Section 6. Exceptions to the rules.
Up until now, the atom seems perfectly ordered, but nature loves a good plot twist. The twist here is all about ultimate stability. It turns out that having an orbital exactly half-filled or fully filled gives the atom a massive stability boost. This is such a huge advantage that some elements will literally steal an electron from their own neighboring subshell just to achieve it.
Let's look at chromium for a second. According to the rules, it should be configured as 4s2, 3d4, but 3d4 is awkwardly incomplete. So what does the atom do? The 4s orbital unselfishly gives up an electron to the 3d subshell. The actual reality becomes 4s1, 3d5. Both are now perfectly half-filled. It's just like a cricketer sacrificing his own century so the whole team can win the match. The overall stability of the atom wins out.
And this brilliantly illustrates that the exact same phenomenon happens with copper. We would totally expect copper to end in 4s2, 3d9. But just being one single electron away from a perfectly fully filled d orbital is way too tempting. So again, it breaks the sequence to lock in that ultimate stability. It shifts an electron, resulting in 4s1, 3e10. It performs this exact rule-breaking trick simply to achieve maximum stability. As we wrap up this explainer, I really want you to think about this. From Rutherford's bounce-back experiment to the cosmic addresses of electrons and the beautiful 3D geometry of orbitals, we are looking at an absolute masterpiece of physics. If this staggering level of geometric and mathematical harmony dictates just one single microscopic atom, what other incredible secrets are hiding in plain sight in our universe? Keep exploring, keep asking questions, and I'll see you in